Okay, hello everyone. So finally we have the last chapter in this class, chapter 10. So further properties of the representations. So in the previous chapter we learned what did we learn? Irreducible, when we have a finite, semi-simple Lie algebra G, we prove this theorem of highest weight, theorem of the highest weight. But the question is, the next natural question is, so suppose that we have an irreducible representation of highest weight mu. So what are the possible weights of this representation, and what are the multiplicities of each weight? So in this chapter, we can answer that question in a certain degree. So in chapter 9, we did many proofs, but in this chapter, instead of giving you proofs, I'm going to tell you the results and application, examples, and how to use this. So in this chapter, as usual, we will assume we will fix this notation, like G is this complexification of this K, a semi-simple Lie algebra, and we assume that there is a inner product satisfying nice properties, and H is the Cartan subalgebra. And we will be using the notation like this. So set of roots and Weyl group, and set of the positive root, the negative roots, and the simple root. So the first three sections, I'm going to be very brief and just tell you the result. In each section, we have one theorem, basically. The structure of the weight. So theorem 10.1. So suppose that we have this finite dimensional irreducible representation of G with highest weight mu. And we already showed that every weight of a representation must be an integral element. And an integral element, so these are the possible candidates for the weight. So an integral element, say lambda, is a weight of this representation if and only if this must be in the convex hull of the Weyl orbit of this highest weight under the Weyl group action. And moreover, mu minus lambda, this is an integer combination of roots. So if integral element satisfies these two conditions, then we can say that that is a weight, and conversely, every weight satisfies this. I think, yeah, I forgot to bring my USB memory, so I'll be right back. Because I want to show you some figures. Okay, so here is the weight diagram of the Lie algebra S of 5C. So weight diagram means, so you can see the dots, many dots, these solid dots. They are the weights of this representation of highest weight given by this circled dot. Can you see that? So this part. So this is the highest weight. Mu is this. And what are the weights? So these are the roots, right? We have, by the way, this is B2, right? So this is C2. I forgot. Maybe for odd, was it B or C? They are isomorphic in this case anyway. So here we have 1, 2, 3, 4, 5, 6, 7, 8 roots. And this is the highest weight. So the Weyl group, if we act a Weyl group on this, then we get this 1, 2, 3, 4, 5, 6, 8 points. So if you take the convex hull, we have this octagon. So every weight must be an integral element. That means must be an integer point or lattice point here. But as you can see, not every lattice point inside this convex hull is a weight. Not everything, only these. Because these are the weight, or these are the integral element that can be obtained from this U by moving in this direction. For instance, this can be obtained from mu by subtracting this root. But because these small short roots, they generate the long roots because this is just the sum of these two. So all you need to do is to go in this direction or in this direction, plus or minus. So because this can be obtained from here by going this one diagonal direction, this is a weight. This is a weight, this. But this one is not a weight because you cannot reach there by going only steps given by these roots. Okay, so you can see these dots are the weights. And in fact, the numbers here written, they mean the multiplicity of each weight. So if it's not written, that means the multiplicity is 1. The multiplicity of these 2 and 4, 5, etc. But how can we compute the multiplicity? We don't know how to do this yet, but we will learn that later, next week. Okay, so the weight, if you know this diagram, then you can tell immediately whether a given integer point is a weight or not, which is very nice. For the multiplicity, we will look at that later. All right. That's for the first section. I'm not going to prove this. And the second one, in fact, we don't really need this, but I think it's worth mentioning this because this is, in fact, a very important object. And it plays a very important role in proving theorems, important theorems like the one that I showed you, and also Weyl character theorem that we will be seeing in a moment. So, definition. Suppose that we have an orthonormal basis. For this K, then the Casimir element. So we have this is inside this semi-simple Lie algebra G. When you have a semi-simple Lie algebra G, we know how to construct this universal enveloping algebra. So the Casimir element is for the universal enveloping algebra G, because it lives inside this, is just by definition, is denoted by capital C. By definition, it's just the sum of all these squared. What is the square of this? Because this means xj tensor xj. So this, by definition, we omit this tensor. Because now this is an element in UG, so it really lives inside this UG. So this is just a definition, but interesting thing about this is that we have this fact. So it's written in the textbook, proposition, in two propositions. And first, we define this element by using this orthogonal basis. But the fact is, it is independent of the choice. The C is independent of the choice of your orthogonal basis. No matter what orthonormal basis you choose, you can define using this formula, but they'll be always the same. And second, C commutes with every element there. So it's in the center of UG, meaning that it commutes with all elements here. And another nice thing, if pi comma mu, so if this is a finite dimensional irreducible representation of G with highest weight mu, then we can extend. We know that every representation of G can be naturally extended to the universal enveloping algebra. So we will think of this as a representation of UG. Then, because now it's a representation in UG, we can apply this C to C. Then this is by definition this xj squared. And turns out that this is just a identity, a constant multiple. So this is a constant, but moreover, we know exactly what this constant should be. This is mu plus delta minus delta delta. And of course, what is this delta? This is the sum of all positive roots, half the positive roots, like that. So we use this notation as before. And moreover, this is always non-negative, and it is 0 if and only if mu is 0. So it has some nice properties like that, and it, like I said, this is an important tool to prove Weyl character formula. But I'm not going to prove any theorems like that, so just you can just forget about that. But I think it's worth knowing this. Okay, that's for the chapter 2 or section 2. And by the way, also a very natural question is the complete reducibility. So the theorem, I'm going to just state the theorem. Every finite dimensional representation of semi-simple Lie algebra G is completely reducible. What does that mean? If V is a finite dimensional representation, you can write this as a direct sum of irreducible representation. Okay? That is what complete reducibility means. So for semi-simple Lie algebra, it's completely reducible, so it's nice. And again, this Casimir element is used to prove this theorem. So we will just accept this and the previous theorem. And today I'm going to focus on section 4, which is the Weyl character formula. So today we're going to be focusing on this, the Weyl character formula. It's a very nice formula. general. It's true for all semi-simple Lie algebras. It's very general. First, we have to define this character. So, definition. Suppose that we have a finite dimensional representation, not necessarily reducible. Finite dimensional representation of G. The character of G is just a function. Function denoted chi pi is a function from this Lie algebra G to complex number given by this formula. Chi pi of x equals the trace of e to the pi x. Because what is a representation? Representation means we go from here to GLV for for this representation. So GLV, so whenever we have an element here, say x, this gets sent to an element, which we denote, of course, pi of x. This is an element here. So an endomorphism. So it's in other words, it's a linear transformation from V to V. So we can talk about the trace, right? And that's just defined to be the trace, but actually not the trace of this, but the trace of e to the this. Okay? E to this. This might seem a little strange because why do we use e? But if you try to remember where this Lie algebra come from, then it makes sense in the following way. So usually when we have a group representation, notice that this is a representation of a Lie algebra. So suppose that G is a group, say finite, not necessarily finite. And this is a representation. So it's a G general linear group. So it's a representation of G. Okay? So usually a representation of a group is just like that. It's a homomorphism from G to a general linear group. So again, here when you have an element, A, this gets sent to an element here, but that's in a general linear group. That means it's a linear map from B to V. So we can, of course, talk about the trace of this linear transformation. Then the character of a group representation is defined to be of pi is given by, it's again the map from G to complex number given by this formula. This is chi, by the way. A. Now it's really the trace of the linear transformation, right? Usually it's defined like that. This is a common definition for the group representation. But for Lie algebra representation, we have e to the pi of x instead of just pi. Because if you remember, we have a natural correspondence between Lie algebra and Lie groups, right? So recall. By the way, we are not going to use this. We will be only using this. But I'm explaining this because why is this natural? To explain why that is recall. Because recall that for a representation, say capital pi V of a Lie group G, we have this corresponding we have a corresponding Lie algebra. This corresponds let's say we have a correspondence with a representation pi on the same space of the corresponding Lie algebra, right? Satisfying nice properties like what was that? I think e to the, okay. What is the definition of a Lie algebra of a Lie group? It's a set of all elements x matrices such that e to the x or e to the t times x is inside this for every real number t. So in particular, if this is in G, then that means e to the x must be in G. In fact, it's true for e to the t for every real number t is in there. So what is the, let's look at the definition and what happens. This, by definition, is trace of e to the pi of x. But if you remember, this is equal to the inside, this is capital pi of e to the x. We learned this in chapter 4. If you have this correspondence, e to the pi of x is capital pi of e to the x. But now, let's write this as, because this is now an element in G, let's write this as A. Then this is what? Trace of pi of A, the usual trace of the operator. This is, of course, the definition of the trace in the Lie algebra, Lie group. So in this way, they are naturally equal. And this might be helpful to remember why this should be defined like that. So e to the pi of x, not just e to the pi of x. It's just e exponential. By the way, you might ask this question, is this well defined? I mean, formally, this is not well defined because this is an infinite series. But it is okay because if this is Cartan subalgebra, this is really an infinite series. But in that case, you can really deal with this infinite series as just using this exponential function. You will see that. Anyway, this is the definition. And this trace, so it looks like a small piece of information about this representation, but interesting thing is that it contains all information of this. The character determines the representation. The proposition, suppose that we have a finite dimensional representation of G. Then first, we can compute the dimension if you know the character. Dimension of V is the character evaluated at a 0 element. And second, because now we know that this representation is completely reducible, we can express this as the direct sum of irreducibles. So if you write this as a direct sum of irreducibles, oh, actually not, this is not. I'm not, Weyl space, let's write. It's not there. Weyl space with multiplicity. From now on, I'm going to write the multiplicity by mult lambda of course, weight lambda. So we know that representation can be written as a direct sum of weight spaces, and this then for all elements in the Cartan subalgebra, H, x pi, if you evaluate that at the this element, then this is summation m lambda. Oh yeah, this will be just m lambda. That's for short. And e to the this. Here, this is really just exponential function that we learned from calculus. Notice that this is a real number. So this part is a complex number. This part is just e to the something. It's a usual exponential function. Actually, the proof is not difficult, so let's see. So first, let's compute this. What's the meaning of this? This is a trace of e to the pi of 0. But pi of 0 is going to be the identity. Oh, I mean, the whole thing is the identity. Because this is 0, e to the 0 is the identity. But what is the trace of the identity? We have this diagonal entry, all ones, so we will just add 1, the dimension times, so it's just the dimension of V. So very simple, right? And second, so let's consider one element from the Cartesian algebra. Then for any x in the vectors weight space, is a weight vector. By definition of the weight vector, this is what? If you apply h to x, then we must get lambda h x, right? For all h. Actually, h is already written there, so I'm not going to write that. So e to the pi h, what is that? What is this applied to this? Because we want to compute this, which is what? This is the summation, the trace of e to the pi x. So we want to compute the trace of this. So to do that, let's apply this operator to x and see what happens. This is going to be, by definition, k from 0, pi h k, k factorial x. So we apply h k times to x. But whenever you apply h to x, you don't change x, but you only multiply this constant. That means if you apply this is always an eigenvector, so we will just get, not, you just change, it's like the effect is like changing this into a just constant. So it's like kx, but this is exactly e to the usual definition of the exponential function. It's like that. That means when we have x, we get x. Only we have this multiplied. So we can take basis from this. Yeah, we can define what's that? Basis using only weight vectors. But if you take the weight vector, then what is the entry there? It's going to be a diagonal entry, diagonal matrix with entry like this, right? It's a diagonal entry. But how many times does this appear? The number of times that appears is just a dimension of this. And basically that's it. So to express that in words, let me write in this way. So therefore, e to the pi of h can be represented by selecting a basis so that the basis elements are weight vectors by a diagonal matrix with entries like this. E to the this appearing how many times? We will select x like a dimension of these times, so appearing dimension of v lambda times. And basically that's it. That means the trace of e to the pi x is going to be summation for all lambda, because these are the diagonal entries, and then each of these term appears this time. So that's it. That's the proof. So the proof is pretty simple. Okay, let me give you an example with this SL2 case. Example, pi irreducible representation of SL2 stay with of dimension m plus 1. So it's finite dimensional. That means highest weight is m, or mu equals m. Then the rank is 1, so the Cartan subalgebra has dimension 1, and we know that this can be taken as the basis. Then every element is constant multiple of this, so we should be able to compute this. This is by definition of A00 minus A. Let me state the statement, and then I'm going to prove it. The trace or the character must be like this. Proof. By the way, another way to write this is sine h m plus 1a, but this is just an elementary algebra. 어디가 빠졌죠? 2? 이렇게요? 그죠. 이거는 잠깐만. Let's see. The definition is like that. It's a trace. If you write trace, then that's now e to the trace pi of ah, or I think if you want to write e, it should be something like that. Is that okay? So here, inside of this trace, we have just element from the Lie algebra. So Cartan subalgebra is also an element in the Lie algebra, so you can write it that way. Okay? But if you compute this, then we will get this. So I'm going to show you how to do that. So what are the weights? I'm going to use this. Oh, by the way, I forgot to mention. This, from now on, we will take this as the definition. This can be taken as a definition. This is an alternative definition of character. This is, in some sense, better than the original definition, because if you look at the original definition, we assume that it's a finite dimensional. Because if it's not finite dimensional, trace, how can you compute? But here, this can be defined for infinite dimensional case. So this can be defined even for infinite dimensional case, right? Because we don't really say any trace here. Because we will be talking about trace or character of an infinite dimensional representation. So think of this as a definition, okay? For finite case, the two are the equivalent. All right, anyway, we will be using this to show this statement. So what are the weights? The weight of pi, we know that these are 1, m minus 2, ... minus m. It decreases by 2, etc. And each of these with weight multiplicity 1. Okay, we learned that. So by the alternative definition, this is equal to e to the, let me write this just to multiplicity e to the lambda h, right? So multiplicity is always 1, the weights are... By the way, this is going to be e to the ma or am, doesn't matter, but let's write that so that it's consistent. And that's it. MA. Just A. Because we write weights in like integers, but this really means this weight equals say J. This means this weight means that lambda with this H, this is J. Okay? Then because in that case, of course, lambda A, this is AJ. So sometimes we write, if you remember, we defined a weight to be just an integer at the beginning, but later we defined weight to be just linear functional. So it just follows from the definition. Okay, so how can you prove this? Let me erase this part. Oh, okay. So the character is computed in this way, but let me let's see what happens if we multiply e to the a minus e to the minus a to chi pi ah. Let's see what happens, because we want to show this. So e to the m plus, if we multiply this to this, e to the m minus 1a plus dot 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 e to the, what is that, minus m plus 1a, and minus e to the m minus 1a plus dot 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 e to the minus m plus 1a, or minus, they're all minus, minus e to the minus m plus 1a, right? Now, as you can see, we have a lot of cancellations. So at the end, e to the m plus 1a, e to the minus m plus 1a. This is sine h, and this is sine h, right? So if you divide both sides by this, then we get this formula, right? What's interesting here is that if you multiply something here, we have a lot of cancellations, leaving only two terms. This can be generalized nicely, and that will be the Weyl character formula. Just remember this. All right, and before stating the theorem, let's recall that each Weyl group element acts on this IT in H. So H is the complexification of this as an orthogonal linear transformation. Right? So it's a linear transformation here, so we can define determinant of this be the determinant of the linear transformation. So as a linear transformation, we can talk about its determinant, and we will write that as the det of this. And because since this is orthogonal transformation, it's a real vector space, determinant, so we think of this as map from IT to IT, so the real vector space. Determinant of this is always plus or minus 1 because it's orthogonal. So now I can finally state the theorem. It's theorem 10.4. It's the Weyl character formula. Suppose that we have an irreducible representation of G with highest weight mu. Actually, not necessarily finite dimensional. Because now we can define the character as the formal sum. Then the character can be computed in this way as a fraction ratio of this W in the Weyl group, sum over all Weyl group elements, determinant of the element e to the W applied to mu plus delta H over WH, determinant of W e to the W delta H. For all H in the Cartan subalgebra, of course, such that the denominator non-zero. Because if this is 0, it doesn't make sense mathematically. This is indeed a nice theorem. It may look a little, it looks complicated, but if you look at the meaning, and you will see that it's very nice. And it explains those cancellations that we had for SL2 case. I'm going to show you that, but we will need this definition. The Weyl denominator, because this is ratio of two functions, so we have denominator and the numerator, and this denominator is, notice that this does not depend on mu, it's always the same, right? It depends only on the G, the semi-simple Lie algebra. So the Weyl denominator of is maybe of G, I don't know, of G is the function Q from the Cartan subalgebra to the complex number given by this formula. Q, H, basically just this denominator, that's what that means. Right? And using this Weyl denominator, then Weyl character formula, it can be restated. Weyl character formula can be restated because this part is Q. Let's move this to the other side. But okay, let me write that on the next page. What I'm going to do is just move this to the other side and then just equate the, just change the formula. So the Weyl character formula can be restated in this way. So QH chi pi of H is equal to summation determinant e to the W mu plus delta H, right? I just rewrote that. Or, let me rewrite this. This is a sum, exactly like this, except we have no mu, right? That's the Weyl denominator. This is what, by definition, is a sum over all weights. So we can write this way: W in Weyl group elements and lambda. So weight of, let's write this way. So weight of the representation of V. So it's V pi V is finite dimensional, or not necessarily finite. So irreducible representation with highest weight mu, right? this means lambda is a weight for all lambda in weight. We sum over all of this. This determinant, and we had here the multiplicity e to the. Here we had. Okay, let me write and then explain. Equals determinant. I'm just copying this e to the. Right? The same thing. I just rewrote it. Just to understand what that formula means. Okay? So the formula can be stated like that. And let's look at the left-hand side and right-hand side. How many terms do we have here? We have the Weyl group is finite, so this many elements there, and then this many elements there. So there are many, many terms here. Right? There are how many terms? So on this side, Weyl group times number of weights. So these terms, right? How many terms do we have? This many terms. Here, this can be huge. It could be even infinite, right? There are many terms. But we have plus and minus because of this determinant. This is non-negative integer. We have a lot of pluses and minuses, and then they all cancel. And then we only have just one term with plus or minus for each w. So there is a huge amount of cancellation going on. So given an element, an integral element eta, say, there can be many ways to write eta as in this form, because eta will appear many times where lambda is a weight, right? So eta will appear many times because you can select carefully mu, lambda, and w, right? But the thing is, Weyl character formula says that if eta is not of this form, what is that? That means Weyl group orbit of this element, right? We have this element, we apply Weyl group elements there. If eta is one of them, then, sorry, let's consider this first. If it's not one of them, then all terms cancel of this form, cancel, right? Because we have nothing there left. And if this is indeed one of the Weyl group elements in the Weyl group orbit, then only one term remains, like plus or minus, right? So there are many ways to express this, but they all cancel, and we have only 1 over 0 term remaining. Just like this. Where is it? Just like this. This is basically Q, the Weyl denominator. This is the character. This part is the right hand or the numerator of the Weyl character formula. We multiply these two as a term. There are many of them, right? But they all cancel, except those that really Weyl group orbit of m plus delta, right? So very interesting phenomenon is happening. Okay, let me give you an example. Let me explain that again using this. So pi, irreducible representation of SL I'm using the same example of dimension n plus 1. And what is R? We have only, it's a one-dimensional, so the rank is 1, so we have only two roots, alpha and minus alpha. So what is delta? This is, of course, the only positive root, so delta will be half the alpha. And let's take, so alpha, h alpha is, this is 2, right? So h alpha is, in fact, in our notation, it should be this, in our usual notation. Just to indicate that this is the root and this is the co-root. And what is the Weyl group in this case? We only reflect once, so it's a plus or minus 1. We have just two elements, the Weyl group. So what is the highest weight? The highest weight is mu, but what this means that if you apply this, this is m. That's what I mean by this. Okay, this really means this. The highest weight. As this is our old way of expressing a weight, but this is the usual way using the what's that? Linear as a linear functional. Okay, let's take this element. Say generally it looks like this, right? General elements looks like this. So this is a 0 0 minus a, and then what is q? Weyl denominator, by definition, this is determinant e to the lambda delta h, right? But we have only two elements, 1 or minus 1. 1 has, of course, determinant 1. In that case, what is delta? It's 1 alpha over 2 h. And if we have minus 1, then, of course, the determinant is minus, and here it's going to be minus, right? What is that? This part is 1 over 2 alpha a h alpha. So that's going to be what? A. Because a comma h alpha is 2. Okay? So this is e to the a, e to the minus a. Exactly the thing that we saw. Okay? And we already computed this. I will just use that. We know this. And what is the numerator in the Weyl formula, Weyl character formula? This is e to the h. But again, we have only two elements. One, we have a mu plus, what is delta? Is a 2 alpha over 2. This is going to be a alpha, a h alpha, minus, and minus of them. And what is that? Mu comma h alpha. What is that? That is m. So this part e to the m, but we have a, so am. This inner product with this, we know that that's going to be a. This is minus of that, so that's exactly what we have seen already. So the Weyl group formula, Weyl character formula works. You can say that this is the proof of the Weyl character formula for this very particular case. Okay? Yes, if you want. So Weyl character formula, QH. It works in this case. This works. What about dimension 2 case? I'm going to show you with this example. Where is it? Just remember this. Remember this. This is the Weyl character formula. Remember this and this. All right. So I'm going to now show you a two-dimensional case example. So, okay. Hopefully you can you read? So, by the way, I'm going to consider irreducible representation of SL3. So it's now rank 2, so the weights and roots, they live in two-dimensional space like this, with highest weight mu, which is 1, 2. So highest weight is like that. And let's see what Weyl character formula says. So we have Weyl character formula says this times the Weyl denominator, and a character is equal to this sum. And let's see what that means. So what is this? We have Weyl groups. So we have, this is the delta, right? This is delta, because delta is just, we have 1, 2, 3 positive roots. We take this and this, the simple roots. So we have 3 positive roots. The sum is 2 times this. So the half of that will be delta. So delta is just this root. So if you apply Weyl group element to delta, then we get these 6 elements. So W dot delta will be one of these. And the sign is written like that. So here, double identity, so its the sign is plus, and here the sign is minus and plus, minus, etc. Okay? So here we have this. Think of this as the sum like that. Imagine the sum like that. And what is the character? By definition is the sum of all weights, and e to the something like that, and then multiplicity. So we know that if this is the highest weight, we consider all the Weyl group orbit of that. And then we know that these solid dots must be the weights. And we suppose that we already know that the weights are multiplicity, so 2, 2, 2. And now if you know this part, just this means we have, this is mu, right? Mu plus delta is what? Delta is this arrow, so mu plus delta will be this. This is mu plus delta. So you apply Weyl group elements, then you get all these 6 points. Okay? And we only consider those with appropriate signs. So what Weyl character formula says is that if you multiply these two, then we get this. But what does that mean? So if you multiply this and this, then we just ignore this and then just look at this part. This is a vector. This is a vector. We add these two together, and we will get another vector, right? So for instance, let's look at this, this circle. This does not appear. Actually, it does appear in this. If you take the product of this term appears, of course, but with many pluses and minuses, they all cancel. Then it will be 0. Because how can we get this? This vector can be obtained by one of these weights. Think of them as vectors by adding one of these. How can we obtain this vector? Because we have only 6 possibilities to move from this delta, from W delta. This can be obtained from this weight by going in this direction. That direction is delta with minus sign. So this is minus. And this can also be obtained from this vector by going in this direction. That is plus. Also, it can reach from this by going in this direction, which is plus. But of course, we have to have this multiplicity. So this has multiplicity 2. So the coefficient goes into this, but with minus sign. But this coefficient is 1, it goes to this, but plus, this plus. So we have in total 1 plus 1 minus 2, which is 0. That's why we have empty term over there. But why is this appearing only once, how can we get how can you reach to this position, this point, from one of these by going in this direction? This can only be reached by going from this, which is over here, in this direction. That's the only possible way. And you can see that is the weight multiplicity is 1, and this is plus. So you can see it has to be, it's the only term, so it survives. And you can, for any point there, you can check that they all cancel like that. That's actually another proof of, or a proof of the Weyl character formula using the diagrams for this very specific example. But the amazing thing is that this is true for all reducible representation of any highest weight mu. Okay, so this example shows that for any, so if suppose that you want to know the weight or term appearing in this character, then you can see for every part here, the way that you can reach to this point is from one of these 6 points in this hexagon. And if you go from here to there, then we have minus sign because of this, because what is that? This, if you want to go, this, I think it should be plus. This is plus, I think this is minus. I think I reversed the signs, but in the end, they all cancel, so the answer will be the same. But anyway, like I did, for any point, integral point there, you can check the coefficient is 0 for every white point. And for every black point, it appears only once with appropriate sign. Okay. So as some homework problems, you will prove or verify by character formula using this kind of argument. So that's one of there will be 2 homeworks like that, homework assignment, homework problems like that. But I'm not asking you to give a rigorous proof, but just arguments like that by drawing some diagrams. But anyway. Let me finish by telling you these 2 facts. This written in proposition 10.16 and corollary. So first, the exponential functions h gets sent to e to the lambda h. For any choice of lambda, so there are many exponential functions like that. They are linearly independent in this function, continuous or C infinite functions from H. That means, therefore, if f, a function inside this space, is if this can be written as something like that, because by the character is one of the functions like that, right? The character looks like that. Then this fact says that the expression is unique. There's only one way to write in this way. So that means you can kind of, if 2, suppose that this is equal to this, then you can compare them term by term. They have to be the same each term. The second, if f is written in that way, So in other words, all that matters is what you have over here. So from this, actually, in some books, character is defined as a formal sum without this. But anyway, if this and we have this property dot fh for all Weyl group elements, and of course all h, and then see, you can compare these coefficients like that. So some function will have, for instance, Weyl denominator will have property like that. That's another homework problem. Okay, so this is for the Weyl character formula, and we don't have class on Thursday, so the next meeting will be on Tuesday, and there will be homework problems on the class webpage, so you can do that, and I will finish here and see you next week.